All right, everyone. It looks like we are now at the start of the next part of the session. Just wanted to make sure with, people there locally that everyone is back in the room and ready to start.
Hi, Pepper. We are ready.
Awesome. Well, thanks, everyone. Glad you all decided to come. And thanks, Matthew, for taking the extra early part of it. My name is Pepper Martz. I am a student at the University of New Mexico under Patrick Bridges and an intern at Sandia National Labs under Matt Desange. And I'm here to continue our conversation about partition communication. My talk will have a focus on porting or design of partition communication with a focus on how to actually handle partitioning structures. So let's start off. So when it comes to actually implementing a fine-grained application or converting an existing application to use fine-grained communication, there are three major tasks. One is having some way to map the data elements that you're using in your computation loop to the communicated partitions that something like MPI partition communication or MPI RMA are going to be sending over the network. The next part of that is doing all of that from a threaded context. Big reason we're doing this in the first place is to handle thread complexity. And then the last part is tuning the partitioning for best performance, whether that is methodology of handling data structures, the size of the partitioning, etc. So let's start with the first one. So when it comes down to it, the difficulty of this process can vary dramatically. Often, what you'll see in publications about this is this coupling of thread completion to marking partitions ready in MPI partition communication. And that's a pretty straightforward process. Basically at thread join, you say, okay, this thread computed this work that's going to be sent over the network, mark it ready, send it. The only issue is that's not necessarily pragmatic for something like Halo communication. Often you're assigning threads in something like an OpenMP parallel region in a way that doesn't necessarily sort of track one-to-one with a partition. For example, let's say you're computing something that falls on the edge of your cuboidal computed volume. Well, that is going to be, you're likely to have multiple threads computing that edge. Each element of that edge is, sent to as many as 1, 2, 3, 4, 5 recipients. This sort of conception of a thread works on a piece of data that is sent to one recipient often starts falling apart in physics codes. So often what we end up doing is instead of thinking about things in this way, instead think about our existing conception of send buffers and start breaking our send buffers into partitions. Then once we have that, in order to mark early, we need to maintain some sort of map from a computed element to a send element in a buffer, and then the partition within that buffer. So we need to start having these data structures to handle this sort of mapping. So just thinking about this in a more concrete way, these are the sorts of answers that you often need to give in partition communication, and we need to design data structures to handle this. So is an element sent? If you're doing your compute and you're trying to mark things ready early, it's good to know whether a computed data element is going to be sent to over the network. If it is, to whom is it sent? And it might be more than one person. If it's sent and you know where it's being sent, well, in partition communication, you're now not worried just about, a send-receive pair. You're now worried about what partition is being sent between that pair. You also have to make sure that it is packed on time to mark it early ready, or to mark it ready early. And you need to ensure that as you are packing elements into this buffer early, that you need to be able to ensure that you know the moment that that individual partition is filled, because chances are there's a decent chance you're going to be doing it element by element as opposed to doing it in strides. So let's think about ways that we could achieve this exact list of needed things. One, just to be complete, is the thread completion-based system. If you have an application that warrants it, the thread completion-based system can make a lot of sense. And this is a system where you determine the completion of buffers based on when the threads working on them complete. If it's one-to-one, this is really simple. If it's multiple threads are related to a particular buffer, you need to start adding in additional data structures. This does require a priori knowledge of the relationship between the worker threads and the communicated buffers. You need to, have the same. You need to be able to ensure that there is knowledge in advance to know that the joining of this particular thread is both known to have happened and the relationship between that and the communicated buffer. That being said, if you do know that and you're willing to create these data structures, it dramatically reduces the potential time, it allows for the fewest changes to an application. So this is really nice. You no longer have to start counting things. You really just have this, hey, look, these threads are completed. Let's mark their partitions ready. It's a very minimal cache impact. You're no longer changing things in the compute loop. Everything is done at the join, and there's real benefits there. The only problem with this is that it has the potential of really dramatically reducing the potential time that can be reclaimed for early bird communication, especially in the multiple thread work scenario. The idea here being, at that point, really what you're doing is you're reclaiming time based on operating system noise, inefficient work sharing, basically just on the time between an early thread completion and a laggard thread completion. And ideally in an application, everyone in the system software to the application development stack is working to make sure that the threads have an even workload and that they all finish on time. So that's sort of a vanishing area to try and reclaim time in. It does exist, but it's not necessarily where you're going to find a lot of time available to reclaim using fine-grained communication. In order to reclaim time between computational completion, of which, there's a linear amount of in a given solve, you really need to use a different method. So one of these is something like a spatial awareness method. In this, we're determining the completion of our send buffers and the partitions within based only on some sort of ordinal system. That could be your row column layer system or some sort of local global ID system. Basically, this is akin to saying, if you can, based simply on your ordinals, on your Cartesian coordinates, determine that we are moving across the face of a computed cube, well, then okay, this face is going to be communicated. If I have, completed an X stride and completed a Y stride, okay, now I know that this face is completed. There are lots of applications where you can figure these things out. There are obviously complexities in doing this, so I'm sure many of you have written codes that do this for conventional communication. It requires knowing the ordering of work and the relationship between local and global ordinals, which is sometimes non-trivial. And it does not always apply well to non-Halo codes, things where there's lots of general communication, like, oh, I have this many atoms that happen to be slipping through at this moment, where there's sort of not this a priori knowledge of the communicated volume. That being said, if you have this ability, it can be nice because it can potentially dramatically reduce accesses of lookup structures, as we'll see in the next scenario. But it does require, a lot more logical work and a fair number of comparisons for each element. And even then, you're not getting around the requirements that are general for partition communication, which is basically counters to ensure that, hey, this partition has been filled, let's fill it ready. Because you're no longer just worrying about, hey, I've computed this face of a cube or this edge of a cube. You're now worried about, I've computed this subsection of this face or this length along this edge, as you now have to in partition communication. So you still have that conundrum to solve. The third and the most generalizable is to create a lookup table, is to, in advance, front load your knowledge of what elements belong to what partition and just figure that out at initialization. So you're no longer worrying about having some sort of logical relationship between your ordinals and your completion. You're not assuming that by completing the last piece of a stride that you've completed the earlier sections of a stride. This is really nice when you don't have to worry about what order threads are finishing computation in. And it's just tremendously generalizable. You can just arbitrarily create these tables based on the needs of your app. The problem with a lookup table-based solution is it requires accessing a lookup table in your tight loop. So if you have a performant hash map and you're willing to take that cache hit, this is an awesome solution, but there is a price you pay for using external data structures in the tight loop of a physics application. That being said, there are a lot of benefits to doing so just from application design and generalizability of construction. So now that we've sort of talked about the sort of things that you need to know in order to do it, and just some sort of high-level conceptions on the kinds of data structures that might make sense or logical conditions that might make sense to figure out when things are ready, you also have to remember that these things are being accessed by multiple threads. And thus, it's not just about having these data structures, it's about having these data structures work in a both thread safe and a thread performant nature. So just thinking about packing and reading in particular, once again, if you're packing at thread join, you avoid these issues entirely. If you're using the thread join model, this is basically a non-issue. But once again, by doing so, you're losing out on a lot of potential overlap. If you're instead working as we're assuming at completion, potentially element by element, you have to be really careful. You are potentially, doing these sorts of operations on an element by element level in your tight loop, and that requires not just thread safety to ensure that you're not clobbering on each other for multiple threads, but it really requires quick access to data structures. In particular, low cache impact and few atomic operations are really important. Ideally, having something like one atomic counter as opposed to multiple atomic counters for example, for multiple buffers, trying to use thoughtful ring buffers that require that have thread safe addition or removal, making sure that you put on your thread safety cap in advance, which sometimes in MPI land we don't have to worry about because we're used to communicating from a single volume. Well, now all that stuff is back in our ballpark. Here's an example from my work in MiniFE. Now, this example happens to come from a code project I work on called Minimod, but the calling structure is very, very similar to partition communication. So here's an example of a WAXB, basically adding two vectors scaled by a constant together. Just a really common linear algebra operation that you might do in an application. You load in your constants, you do your multiplications, you add them together, you put them in a buffer. It's like 5 lookups, 2 multiplications, an addition and an assignment per index. And so, this is very straightforward, very readable, very fast. However, when you start, if this is the point at which a data element is completed and ready to be sent, as it is in MiniFE's example, things can get a little more complicated. So here's an actual code example of what I have done to determine readiness, pack, and actually mark ready of partitions. So now we go from this incredibly simple example to loading in more global information by actually loading in the matrix as opposed to the global matrix as opposed to just the vector. We are now doing an actual test on is sent. So for example, right here, right here, we are trying to shortcut this entire thing if possible, because most of the time your communicated volume is scaling linearly while your computational volume is scaling geometrically. And so what we're trying to do is we're trying to make that assumption that, okay, most of the time we're not going to be doing any packing. We're not going to be doing any sending. We're not going to be doing any atomics. So let's try and have our shortcut happen as quickly and as fast as possible. In this case, is sent is a hash map, and we are just trying to really quickly shortcut this. It's not ideal, but this is a relatively performant way of minimizing your impact on the compute loop. Then once you're in here, you're basically saying, okay, this is sent potentially to multiple people. And for each peer that you send it to, you collect information, ideally that you've computed in advance, so that you just have lookup tables for this. So you're minimizing computation in the tight loop, and you're just accepting some cache impact. Look up your information, pack your information. We're no longer able to just do these monolithic packs at end of time. We now need to basically say, for every element, we don't know whether it's necessarily going to be the element that fills a buffer. There could be other threads working on this buffer, and it's better to pack piece by piece potentially than by trying to have some system to figure out exactly which thread wrote the last element. So we're packing piece by piece. We are then updating our local count of how many elements are in that buffer. This is important. Basically maintaining some conception of the fullness of a partition. In this case, it's an atomic increment. We then compare this atomic int with our expected number that should be in that partition. And if we see that it is filled, then we actually do our ready call and send the buffer. So once again, really simple, really fast, really cache optimized into something that if you happen to do this, which you do infrequently, it has, a lot of call overhead. But these are the prices you pay for reclaiming a substantial amount of unused network resources. So sort of just catching back up on what I've said, there's sort of two takeaways so far in the talk. That's determine partition ready conditions quickly, and ideally don't slow down communication or computation to improve communication. And also do your best to maximize the reclaimable time. Call your readies early, ideally at element completion, as opposed to at thread completion, because that's where we're actually gaining performance. It's a lot harder to reclaim a lot of time for communication from thread differences as it is from element completion differences. Second thing, it's really, really important to, from the ground up, design thread-safe data structures. So really minimizing locks where only one thread can be at a time. And that includes things like minimizing atomics. And if you can, use performant atomics libraries. Simultaneously, if previously you'd been doing additions to some sort of array, if you can ensure that your array accesses don't trample each other, or if you have to have something more like a list, using a thread-safe list implementation like a thoughtful ring buffer. Many applications require really pretty substantial changes to enable this fine-grained communication in a way that actually meets these criteria. But you can do a pretty simple implementation pretty quickly. It's just when you start worrying about thoughtful use of threading, of thoughtful use of thread safety and early completion that things really become tricky. The next part is that you really have to balance the aggregation of your partitioning / binning and how you send them over the network. The actual performance impacts or potential benefits of using early bird communication often are tremendously sensitive to exactly how many partitions and when you're sending them over the network. So, I mean, this is a pretty high-level description of a really big problem of message aggregation and message sizes. But the general dichotomy is this, and Matthew brought it up a little bit in his talk. If your messages are too big, there's no early bird perceived bandwidth bump. And this is because basically if your messages are too big, the total time in application that you could have to reclaim is smaller. So for example, if you have lots of little partitions, well, you finish that little partition, the first complete, probably, in the first 5 to 10% of computation. And thus you have 90% of your compute time to handle the overheads of that send, to send it over the network, to get ready for the next send. But if you're doing it maybe into 2, you've now cut your available time in computation in half to actually have reclaimable time. So you've got that problem. Then on the other side, if your messages are too small, well, now you are latency bound. You are not necessarily actually saturating your network and getting the full bandwidth of the hardware. You also have all the issues potentially, less so in partition communication, but potentially in other communication methodologies of higher matching queues, just generally higher overheads depending on your library utilization. There's lots of potential issues that start compounding when you start calling to the library that number of times. So you really do have to tune message granularity to try and find a sweet spot, both for your application and for your network here. We will go over a little bit of this in our interactive session 2, but I just figured I'd open it up for questions before we move on to that.
Thank you, Pepper. I'm looking at the audience if we have any questions from the audience at this moment. And I don't see any raised hands. So I think we are looking good. And Pepper, feel free to continue whenever you like.
Awesome. Thank you. Let's see. Matthew, would you like to take over the screen share?
Sure. Okay. We have a bit more of a setup this time, and this should be a better starting place. So what do we have? In here, this is kind of based upon the example 1 or the test 1 from the MPI Pittle library. And we're just going to walk through a couple of the processes to convert this from send and receive to partitioned send and receive. So we're starting off, we don't have any multi-threaded communication right now, but we're editing it with a thread just for ease of this. We can ask for multi-threaded later. But what we generally have here is for 10 iterations, we're going through and setting up a buffer. This is just garbage right now, or garbage because we don't, for the purpose of this example, we don't care.
Yeah, just funny work.
Yeah. We're doing an ISend and then we're doing a wait, as you would do. And the receivers just is a one-directional kind of bandwidth style benchmark in a sense, except for it's not doing benchmarking for the most part. But we have our iReceive with a wait, and we can see if we do a Twitch MPI run of this, ignore the cruft, but the we had an output. It does the communication just fine. But the first step that we need to do when looking at partition communication is starting to look at persistent communication as an intermediary step, right? So one of the things that we've talked about is that partitioned, similar to persistent communication, is kind of leveraging the fact that we are reusing the communication setup for multiple similar communications. So in this sense, we can start by doing a send init here. And that should have roughly the same function call signature as isend, right? We're still taking in the buff, we're taking in the size, we're doing the data type, the destination, the tag, everything's going into the send init, but it happens outside the loop. From there, we don't need this isend anymore. And we'll replace that with an MPI start. We feed in the request. It's an important thing to note that both send init, so all the persistent initialization stuff or calls, and then the MPI start are both non-blocking and are non-blocking for all the requests. So even if you're doing like a persistent collective, you're going to need to do an MPI wait. And that should get it ready. Now, the thing for persistent point-to-point is that it is interoperable with regular point-to-point, which is not true for persistent or partitioned communication. So if we go out, we haven't changed the receive side at all. And I need to give that a pointer. If I do that, this should still work the same. And we see the same output. From there, we can start looking at the receive side in the sense of, or we basically do the same thing over here. Has the same function signature as MPI receive. And I messed up where I was doing that. I receive init, and we can get rid of this. We then do an MPI start here on the request. Now, if we were doing a real application, what's up?
Oh, just REQ as opposed to request.
Oh, yeah, that's fair. If this were a real application, we would do some computation here. But the thought here is the same, right? MPI start is the equivalent of posting a receive with everything that you've passed into MPI receive init. So if we build that from there, it should do the exact same thing. Now, where it gets tricky or not tricky, but where this is going to move up in complexity is when we start moving to partitioned communication. Primarily because part of working with MPI Petrol is that we're going to need to have, or we're working on an external library that is built on the premise of not clobbering the internal MPI functions. So if you're using MPI Petrol, you could theoretically use it on top of an implementation that already has partitioned communication. But that requires using the MPIX, so for the MPI extensions thing. So we need to change the request. This MPI send init needs to become an MPI X P send init. Yeah. And if we look at the function call header, we notice that there is one additional input, which is just partitions, which we have already brought into this example as endparts. But there's a problem here, which is to say that the way that MPI partitioned communication is defined is designed around the idea of creating equal-sized partitions, and thus the input for size is no longer your buffer size, but actually your the size of each partition. So to get this, we need to create a new variable count that is simply the buffer size divided by the number of partitions. And then we can move this over to
count.
Yeah, count. Apologies, I'm still not even, it's just past 9 here, and I have not had enough caffeine. Now we have the start, but in partitioned communication, the start no longer that has anything to do with transferring the data. So we need to do it every iteration, but it needs to be done before any call the P ready is made. So if we were to we can move it up to the top. Now, this isn't what you would want to do, but if you were to do this after, say, all your computation is done, so we start off with still maintaining the bulk synchronous model, we can have a pragma. I'm not spelling things correctly. For I equals 0, I is less than. So we want to do for, or have each part sent by a different thread in this case. I is less than n parts I plus plus. And we can do a MPI X P ready. If you were to use any other implementation, you'd drop the X and the request would be the same as your regular MPI request. But if you did in the request, so the I is specifying the partition number. The request is obviously specifying the request. And so this should be all we need to do for the send side to move directly over to partitioned communication in this example. Now, if we move over to the receive side, we need to do similar things. End parts. And we need to change buffer size to count again. But we don't have, and we need to move these, MPI. One of the caveats with, again, working with an external library is that all of your calls need to be in the MPIX. This means that your start call is no longer the same as MPI start. Same with wait. But there's one.
Let's see.
That is, so Sayan has a comment, and we'll pause to address it real quick. Receive side computation before MPI wait. I thought that the receive side buffer cannot be touched until wait returns. That's correct. We're not, when I say do computation here, it's not early computation. It's unrelated computation, right? So in the idea of posting your receives early, you should start to post everything at the beginning of the loop.
Yeah. Also, if those receives were pointing at the same buffer you're using for computation, that would obviously be problematic. But if that's something like an explicit receive buffer, then there's no issue.
Right. And so, provided I didn't get anything wrong, this should do the same thing that it was doing before. And there's a chance that, all right.
Hey.
It works. Now, this gets us to a point at which we have technically implemented partitioned communication. Is there any benefit here? Not really, because we're still in a bulk synchronous model. If we wanted to do something more intelligent in a sense, or not intelligent, if we wanted to actually have individual threads do their own P-ready calls right after the data is ready, we'd need to restructure our loop. So we need to have two-level loop in this case. So let's grab another variable. Actually, we need this to be private to each thread. So we'll put this inside here. Okay. So we want these to be equivalent to the first set in combination. So if we're going through this, we want this to be, or we want a different OpenMP thread for each partition. So this matches up with a lot of the current experiments around partition communication. Is this thread model. Now, if we have our inner loop, we need to then iterate over every element in the partition. So we set that up. And now we need to adjust what we're now we need to combine these two into a single index. So if we have an index variable, our outer variable is I, we multiply it by the total size of the each inner variable and then add that back in. So this should roughly correlate to each partition is being looped over for using the I variable, and every element within that partition is looped over using the J variable. And we can move this into index and index. Now we have two of the same loops essentially. So we can grab this p-ready call and move it into here, which should allow us, or does a p-ready after we compute every element. So if we run this again, we get the same thing. But now if any of these are delayed for any reason, we should start to see a some early bird communication. So to kind of emulate this, what we can do, because this is a really, this is a toy example, we're not going to see a lot of variation here. Not there. We wanted to do it. So up here, we can kind of inject some noise into our main thread. If we have, so for thread 0, this is an extreme case where we're sleeping for an entire second on one thread, which is unrealistic for sure. But it will kind of, through nanosleep or whatever, we can slowly get closer and closer to mimicking some of the observed system noise that we've seen, which is much, much smaller than this, or load imbalance, or what have you. Another option we can do is to make, because our number of parts is currently tied to the number of threads, we could look at this from the perspective of increasing the number of parts to have to double what had before.
Mm-hmm.
So that each thread is computing two different sets of data. That's another way that you might see variation here. Other things we can do here, if we, let's make sure that this still works. Let's see where sleep exists. What do I need? We'll just delete the sleep for now. As it's kind of
yeah, it's just a toy example anyway.
But if we were to do, or if we wanted to do early bird or early computation, one thing that we could do is start looking through the partitions again, and instead of doing a P arrived, we can do, or P ready, we can do a P arrived. So this would be the equivalent of, this is the receive side partitioning. So we need a flag. Let's, oh, whoops. If we look at
request partition flag pointer.
Okay. That is not the order I would have remembered off the top of my head. So request.
Partition is a raw int, and then flag is an int pointer.
So partition, so if we do I here, and then flag would be
At flag, yep.
And if flag, or if you want to be explicit about this, so if the flag's set,
Do work on partition I.
yeah, do. So that's a really, simple example. There's an attempt to, or I forget all the arrived variants that are currently implemented in the standard, defined in the standard. There are tickets being worked on that add in stuff like P arrived any, and P arrived range and stuff like that. But in general, the initial implementation focused way more on send side partitioning. But it shouldn't change anything in our, that I missed a letter there. This shouldn't change anything in our result Um,
Yep.
It's important to note that p-arrived is a progressing function. What this means is that you could theoretically say if we define flag out here, oops. Yes, that was one of the things that we had to just have had a lot of debates about, but my understanding is that p-arrived does guarantee progress. And it certainly this was an issue in the OpenMP implementation. So iterating or reading the question for everyone who's not looking at chat, does p-arrived guarantee or progress? And the answer is yes. As far as the spec is concerned, it does guarantee progress. There's some nuance there in terms of like why you might not want to guarantee progress, but that's what we're getting at here, is that we could theoretically and if we have int I equals 0, we could let's just get this done here. We could take I plus 1 modulo n parts. And then we can change this to we change this from a for loop to a while loop. We can we could theoretically have it something that looks like this, where we kind of go around the different partitions polling, because p-arrived is not a blocking call. It will return the current status. So think of it like an MPI test for individual partitions. As you can have a modality where you're looping around until one partition is finished, and do some amount of work on that, and then jump out of the loop and wait for the rest of the request. Idea being that if you assume you only have time for one partition to actually get work done, there's that. It's, there's a lot of nuance here, and we haven't explored a lot of the different ways to use this in real applications. The p-ready is much more straightforward in terms of implementing in applications. P-arrived, not as much. Let's see if it still works. Okay. So, yeah, that is how you use p-arrived. One other thing that's not currently implemented but is worth mentioning is the proposed pbuff prepare, or I'm not sure of what we've currently decided on, but this is in discussion at the forum, and this is I don't think is implemented here, but or prepared. This is an optimization that's been then proposed for GPU communication. You look at this and you see that this allows you to have a two-sided interface to what acts behind the scenes as one-sided communication, right? You have you don't have to do matching every time, so you can just set up a buffer, all this other stuff. PBuff prepared is implements a bunch of stuff that we would have had in MPI start if MPI start were allowed to block. And what this means is that it's kind of a let's see here, finish buffer. The idea here is that it's kind of a one-way collective almost, in the sense of the receive side never has to wait on it, just the receive side indicating to the send side that it's ready to receive data. And so the send side blocks on this PBuff prepared call until it's ready to send. And this allows us to get rid of a lot of the branching conditions in the internal implementation, which makes a lot of sense for internal GPU implementations, right? So we don't have to worry about sending data before the receiving buffer is ready, and track state on that and all this other stuff. If we have this, it allows us to get rid of it. It's not required for partitioned communication, and we're not going to, no one's proposing to break current partition communication. The one thing that might change is that we're looking at having specific initialization requests that require PBuff prepared, so that we can even reduce state even further. But I think that covers almost everything. Pepper, did you have anything that you wanted to add at this point?
Sure, I'll add a little bit. If anyone was wondering in my talk why I was describing atomics and additional data structures, part of that is based on the fact that in this, it's sort of the implied computation is predicated on, okay, we're going to allocate resources to work on partitions. It's doing computation based around the communication considerations. In a lot of your applications, either the actual computation you're doing or just the nature of your development is not going to put communication first in the decision-making of application design. And thus, you may have a situation in which you're not going to conveniently have threads finishing partitions one by one, but instead lots of threads working on lots of partitions in unpredictable ordering. And thus why you need to do a lot more checking and a lot more bookkeeping. The only other thing is we have 1 minute left before we want to cede over to Jan. Are there any other questions on the programming we've been doing right now? Awesome.
Yeah. As Pepper mentioned, this is a toy example with, if you can get, if you, depending on how you decompose your problem to your threads, you can either have this really neat or kind of partitioning that is directly relates to this, but that doesn't work for every application. And we know that. And okay, so MPI Advance is a project out of the Tufts ECS PSAP Center, which we collaborate with sometimes and have collaborated a bunch in the past. It's run by Tony Shellum, Puri Bangalore, Patrick Bridges, Amanda Beans, who I'm sure many of you who are there have seen over the course of this week. The question that came in from Evelyn was, so what is the role of MPI Advance here? MPI Advance is a project of building external libraries to implement research level features in MPI. And so the idea here is that like MPI PCL was kind of the original part of that, where even before we had MPI 4.0 released and had an OpenMPI implementation, there was a library, MPI PCL, that you could bug Tony to get and download and start writing your partition communication code. There are some caveats there that, it's research code, but that is the role of MPI Advance.
Yeah. And it's also an external library as opposed to, having access to the internal MPI data structures. So there's a caveat there as well.
There's a caveat there, but it's also portable and can be layered on top of old versions of MPI, right? Or current versions of MPI, depending upon the feature, right? Like OpenMPI 5.0 is going to be the first release that has any sort of partition communication implementation available. But if your system runs OpenMPI 4.1 or an earlier version or a vendor version that hasn't pulled in the newest source yet, like Spectrum MPI, that this allows you to have access to those features. Does that make sense, Evelyn?
Yes.
Okay. So let's pass it over. We're about 3 minutes late. Sorry, Jan, but if you want to take over.
Very good. Yes. Thank you.
Pepper and I will be on the chat. If anyone has any other questions, feel free to ask.
Good, very good. So hello and welcome to the third part of our MPI tutorial. Matthew or Pepper, is my voice audible over Zoom?
It is audible over Zoom. We are seeing presenter view on your slides.
Mm-hmm.
So if you wanted to, I don't know if there's a switch. They're readable.
Yeah. Also, is anyone in the room or even not in the room actually remotely interacting with this? Or is this just an issue for you and me, Matthew?
Oh, is anyone watching the slideshow? Other than us, I think so. Yeah. So let's get if we can get the slideshow up. It'll be fine in presenter view. It's still readable. It's a little bit smaller.
Yeah. Good. So hello, everybody. Also, hello, everybody who connected over Zoom. It's good having you here. I see still we have a lot of, quite a good size, a lot of attendees here. So you must be really a hardcore MPI fans for hanging in for such a long time and being here. So it's good to see that. So I will be talking today on advanced threading features in MPI. My name is Jan Šieško. I am member of staff at Sandia. I work mostly on as a dev in the Cocos Core team. I also lead the development of the user-level threading library called Qthreads. And I also took over maintenance of user-level or threading support in OpenMPI. And this happened a couple of months ago, and this was a good opportunity to take a look what MPI thread multiple really means as an execution mode in OpenMPI, and to think about, okay, how is MPI supported currently when being invoked from a threaded context? But the new consideration here is, what are the implications when MPI is invoked not only from a threading context, but from a tasking context? And who of you know the difference between a task and a thread, or a user-level thread and a thread? Are these terms that are known to you as the audience? Very good. So there are a couple of considerations that make this interesting. And MPI, of course, supports the thread-safe execution mode for many years. There has been a lot of work on the execution modes, MPI plus X, MPI everywhere versus threading and MPI. However, with the advent of tasking, new properties come up. And the key property here with tasking is that the unit of work, the concurrent or parallel unit of work, comes comparably cheap in comparison to threading. And so this gave a little bit of more momentum and uptake regarding this topic in the community, and this motivated also the talk and to be here to discuss this. I have prepared a couple of topics for you today, so I will start with a problem statement that should illustrate what the fundamental issue is when we combine MPI and user-level threading libraries or tasking. I would like to show you solutions that are out there today on how to deal with this. So it's not a problem that surprises us. We have seen this coming for quite a bit of time, and we have three main directions on how to resolve the issues that I will be showing. So I will list these techniques as much as time allows, and then I will summarize. So in my first slide, okay, let me see if I can close this upper Zoom bar, but it seems I cannot close the Zoom bar up here, but that's fine. So here I'm showing an example where I have a bunch of tasks that I instantiated, and the scheduler placed them in the ready queue. This is independent of any programming model. The only important thing is that these blocks that you are seeing here are tasks. And I have now an execution scenario where I have two ranks, and on each rank, I instantiate a couple of tasks. Now, the scheduler places them in the ready task queue. So they are there, and they are subject of being scheduled and executed. Now, in this scenario here, I have to comment that all the tasks are independent of each other. So they receive as an argument, which is of this task arg's argument. And they are free to be scheduled in any order as the scheduler sees fit. And if you take a closer look, I have green and red tasks. Green are tasks that send data. So an MPI send is an operation that doesn't block on a blocking condition coming from the user code. So it can block internally on resources, but not something where the developer would cause that blocking state. And then I have some tasks in the red rectangles that include an MPI receive call. So we see first that we are calling into MPI from tasking library, and we see that these tasks can be scheduled in any order. Now, who sees the problem here that can arise? Who can see the deadlock situation here? Well, there is a potential deadlock if, for some reason, the scheduler on the rank 0 decides that the red task will be scheduled prior to all other tasks, and there is one additional condition that has to be met, and that is that the number of threads is smaller than the number of tasks. Because if it's equivalent to the number of tasks, there is a high probability that these tasks will run in parallel. So we will not see this deadlock situation. However, if the ordering is such that red tasks happen to be scheduled prior to the green task, we have a deadlock situation. The keyword here is that tasking is considered a cooperative threading model. That means that everything that is included inside a task, that is captured inside a task context, has to be cooperative. Now we see that the blocking calls, and there is the example of an MPI receive, is not cooperative. It doesn't cooperate nicely with user-level threading libraries. So we need to deal with this. And my talk is basically to show you and to explain how we are tackling this, how we can guarantee some progress in your application when MPI is invoked from a cooperative multi-threading library. So when we are looking at the support of tasking and MPI invocation out of tasks, we have three directions of thought that are on the table, and we haven't decided which one is the best or which one is the dominant one or which one will be existent 10 years from now. However, these are three techniques that I think is important to be aware of, especially if you ever in your life write an MPI in its thread or MPI in it with MPI thread multiple and work with modern programming models such as OpenMP tasking or Argobots or Qthreads or StarPU or OMPSS or you name it. The first thing is user-level threading support in MPI. So there is a thing called the user-level threading support in MPI. That's the work that we have been working on with Matthew as well and Pepper to add user-level threading support in MPI. It's basically what the name says. And what it is, so it's a feature block in OpenMPI and in MPIG as well, starting with these versions, which implement functionality to guarantee progress when being invoked in these scenarios that I showed previously. And to work with this feature block, you can simply download one of the supported MPI implementations, which are listed here. And then you can configure OpenMPI or MPIG to support one particular user-level threading library. So currently, this technique doesn't support them all. So you have to select which user-level threading library you are going to use in conjunction with your MPI implementation. Configure it and configure time, make it, build it, make it, install it. And the flags are listed here. If you have an OpenMPI or MPIG installation, in this case, OpenMPI installation, you can type in OpenMPI _info -config, and it shows you the configuration options. And there you see what the threading level is. So we include that in the configuration dump that you can obtain through this call. Now, under the hood, what does it mean? So what does it mean when I say progress guarantees? And what does it mean when I say it only works with one particular threading library? So what we did in order to guarantee progress is relatively simple, and it works surprisingly well. What we did is we encapsulated everything in OpenMPI. So I'm now speaking in particular about OpenMPI. We encapsulated everything that could potentially block such as synchronization constructs into generic header file that basically lists a whole bunch of declarations around mutexes, logs, conditionals, signals. So these are the 4 feature blocks that can be invoked in OpenMPI internally in order to handle state, protect state, etc. So we added the header, a generic header that lists the declarations for all synchronization constructs that are internal to OpenMPI. And then we added one more thing that is important. We added this extra line that is marked here in red, and the comment as well, called Opal thread yield. And the Opal thread yield, so it's the open platform abstraction layer or OpenMP platform abstraction layer, adds a call again to a generic interface function called the Opal thread yield, which yields the current executing task back to the runtime. So we have done 2 things. We have added basically a generic header file that would implement the locking mechanisms, and we added an additional call in the OpenMPI progress engine to call into the task scheduler in order to give the task scheduler the opportunity to yield the current task or to stop the execution of the current task and schedule another task instead. Now, I have jumped, I think, too quickly over this slide. So this slide shows the implementation of that generic header file. And here it shows one implementation. I think this is QThreads. So here it shows how the generic header file is implemented using the QThread API. So there is a QThread spin log in it. There is a QThread spin log lock. There is a try log, etc. The important thing is that we now offer an interface, and we allow at compile time to compile the interface with an implementation that is specific to the threading library. This avoids situations where we would call into MPI, and MPI would decide, for example, to block on an internal data structure, which would block the calling task. If we have an implementation that is aware of the threading model, in this case that is QThreads, it is the responsibility of the threading model to not block and not cause any deadlocks. For example, here the QThread spin log lock would internally yield the execution of that calling task and invoke the task scheduler in order to schedule some other ready task in order to guarantee progress. So these are two additions that we added. One is the implementation of the logs. One is the addition of the periodic polling into a task runtime in the main OpenMPI progress engine. Now, this works only with user-level threading libraries such as QThreads and Argobots. These are those that we have added, but it's surprisingly or interestingly simple to extend this to support any other user-level threading library as well. This is not a model that would be typically supported by OpenMP because of different considerations there and the execution model of OpenMP tasks. So for OpenMP, we will need a different technique. Now, we have implemented a benchmark suite called the MPI Partix benchmark suite, and I invite everybody to try it at some point. So the name comes from, as you can see or imagine, from partition communication. So it was a benchmark suite that we initially developed to benchmark partition communication. However, in this talk, I'm not talking about partition communication, but about tasking. And it happens that this benchmark suite abstracts from particular task implementation. So we would have OpenMP task. So in this case, you can experiment with that as well. So there is an OpenMP backend, there is a QThreads backend, there is a pthreads backend. and there is a Argobots backend. The API is simple. It allows to generate basically a task called a Partix task, and then there is a task weight, and there is the notion of a context. So you can basically task weight on all those tasks created in that given context. Now we have one example that is included in MPI Partix that is specific to support the idea that I'm presenting today, which is the correctness test. And the correctness test basically instantiates a whole bunch of tasks in different orders. So I'm having on the left-hand side a loop that loops over a couple of Partix task instantiations. And then on the right-hand side, I have the bodies of those tasks, and you see that I have sending tasks, receiving tasks, and there is one blocking called the MPI weight. So with this application, you can easily benchmark and test if your implementation will deadlock or not. If it deadlocks, then something is wrong with either you or most likely the OpenMP implementation doesn't support user-level threading. So the progress is not guaranteed. We have tested MPI Partix with different benchmarks that are included. And here, even though these are results that deserve discussion of partitioned communication, I will not discuss a partitioned communication right now, but what you can see here is the cost of the creation of concurrent or parallel work. So here on the left-hand side, I'm showing the achieved bandwidth rates over different buffer sizes using p-threads. So where the backend in Partix uses p-threads. And then in the middle, I'm showing the same thing where the backend uses q-threads to spawn parallel work. And then on the right-hand side, I'm showing OpenMP tasks. And you can see that I'm achieving more or significantly more bandwidth when I can create that work quickly. So you see that the performance grows steeper already for buffers that are smaller, because the overhead of p-threads creation and p-thread handling is not given. I would like to use this as a motivation to consider tasking as vehicle for concurrency and to spawn off concurrent tasks, especially if we have support in MPI, because simply nowadays the overheads are so extremely small and support the massively parallel architecture so well. Good. The next technique that we have, and I think if I can communicate these two, then I would be happy to do that in my time, is called user-level threading support through MPI continuations. Who of you has heard something about MPI continuations? Very good, very good. Okay, MPI continuations represent a very important development in MPI, where MPI is gaining a new property called event orientation. And that is extremely important. It would allow to define callbacks on event completion. So even though I list here the API, the key takeaway here is that with MPI continuations, I can register a callback function to any given request. Now, when the request is satisfied, OpenMPI or the MPI implementation automatically invokes that callback. And that's a cool thing, because suddenly I can support user-level threading with these features, and I show you how it works. The new API additions is MPI continue init. So you initialize an MPI request object that is going to be your MPI continuation request. We call it like that. And then by MPI continue and MPI continue all, you associate a callback to an operation request. So operation request, we call requests that come from an operation. Now, remember my red and green rectangles from the previous slide. So in order to use continuations, this doesn't come completely cheap or completely free like with the previous technique, where we added the polling into the OpenMPI main progress engine. Here, you will need to do a little bit of code refactoring to get this done. And basically what you need to do is take your blocking take your task that includes the blocking call and add continuations. And to do so, you have to split your task into a task that issues the operation, and then into a task that would consume the data that comes in once the operation completes. So you have to split up your tasks to do this. And I'm showing it here. So we have an upper task and a lower task. The first task is called task receive. It initializes a continuation request. It then calls into MPI IReceive. So we changed now the blocking call into a non-blocking call. And then we associate this request of that IReceive with the continuation request. And we do this in the MPIX_continue API call. One additional parameter that we have to give it is a callback function. And the callback function here is the release event. So now when this task runs, so task_receive runs, it runs to completion. So it's done. But then the registered callback is activated once MPI IReceive has been completed. We can do it, for example, through an MPI test. And what it does in my callback, I do something like runtime associate event and my task. Okay? So you see the callback that will be called once MPI IReceive completes. So the data is there. I will call a callback called the release event, and there I somehow, independently of your tasking implementation, will say, okay, now my task receive continuation task can be scheduled for execution. And that task receive continuation task has, for example, a printf where we print to the screen the data that we have received. What is the cool thing about this? This is the way we would like to support tasking and MPI in OpenMP. So here, OpenMP, basically for this purpose, adds a new clause called the detach clause that you can apply to the task construct. And everything else is as I described before. So previously, when you had an MPI receive call that would block your task and thus eliminate the progress guarantees, now you are using an asynchronous MPI call, the MPI IReceive, or a non-blocking call. You register a continuation. Basically, you would say that you register an event to operation request. And then here, I'm also adding a couple of depend clauses. So this is, for example, interesting to those of you who have programmed or expressed data flows in their applications using the OpenMP depend clause. Has one of you tried to program or to express a data flow using the OpenMP tasks? Very good. Okay. Yes. So OpenMP supports a depend clause where I can say, okay, this task is going to have an output dependency over some variable, and another task will have an input dependency over that variable. And now it is up to the scheduler to guarantee that these tasks are executed or scheduled correctly. That is, that the producer is executed prior to the consumer. Now, with the new clause, the detach, I can defer the execution of all dependent tasks conditioned on that event. So that means when the IReceive concludes or is satisfied, the condition for the satisfaction of IReceive is met, then this detached event is met and the dependency between these two tasks is also met, so the next task can be scheduled. So basically, with the detach clause, OpenMP supports external events in their data flow graph. there is one particular interesting thing, which is here this additional task that I had to add, and this is an interesting thing, and the OpenMP community is working on this currently. In order to guarantee progress, somebody has to periodically poll into MPI in order to have some thread executing the progress loop. If there is nobody executing the progress loop, then there will be never progress. So right now the workaround is to add this additional task that has to be scheduled somewhere, and in this program it's guaranteed to be executed because there is nothing that would block it prior. And we call into MPI test. An MPI test is exactly the call that we do in order to progress MPI in respect to to that particular request, but also all other requests. So we process everything in that call. Currently, OpenMP, the OpenMP language committee is taking a look at free agent threads, the concept of free agent threads, which basically represent unshackled threads that can be implicit worker threads that could implement functionality like this. The last thing is, okay, the callback here for OpenMP uses a new API that is called OpenMP fulfill event, and basically that would associate the status to with an event. Okay. The final technique that we are looking at is basically API overloads for proprietary event handling. And there is one library that has been developed and that started also quite a lot of thinking in the direction of how to support tasking with MPI. It's called the TAMPI library, the task-aware MPI library. This originates from the Barcelona Supercomputing Center, where colleagues started to think about this around 10 years ago, where at that time, the idea was, okay, what happens if we create a library that overloads, that you can LD preload, let's say, with your application, that would intercept all MPI or relevant MPI calls and do some magic such that we would guarantee progress. And this is exactly what the TAMPI library does. And it works exactly like MPI continuations. However, it is proprietary specific to the OMPSS programming model because that's what has been used in order to showcase this technique. But it's exactly the same thing. It uses a counter. It associates dependencies with events. When events are fulfilled, then dependencies are fulfilled, and then dependent tasks can be scheduled. So this brings me to my summary and outlook. So I would like to communicate that solutions exist to guarantee progress. To support the blocking calls, you have the option of using the OpenMPI or MPICH feature, which periodically polls on blocking calls and locking data structures that are internal to OpenMPI into the task library. Or you can use overloads such as TAMPI, which are typically specific to some programming model. If you have non-blocking calls, that is, you change your blocking calls into non-blocking calls and split tasks such that a dependent task can be invoked once an operation request has been fulfilled, then you can use MPI continuations. We have the MPI Partex benchmark. We will branch it off and we will call this thing MPI ThreadX or ThreadX. And it will include applications that will specifically benchmark threading and tasking with MPI. So we would like to port the OSU benchmark to use continuations, to use the techniques that I showed. We have a couple of more applications ported already. And the objective is basically to quantify what are the implications of these techniques in HPC, especially thinking about the latency that is added when suddenly a blocking operation becomes non-blocking, and the progress of your application depends also to a big extent on the scheduler. With this, I'm listing a couple of references, and feel free to ask any questions. Thank you. Very good. So I see there are no questions from the chat. So with this, I would like again to thank everybody also who connected over Zoom and to everybody who is with me here in the lecture hall. Thank you for the attendance. It was great having you here. Thanks for attending the MPI tutorial. Also, thank you, Matthew and Pepper, for your previous sections. And I hope to see everybody next year. Thank you.
Thank you, everyone.